Now the program I want to demonstrate to you here doesn't really do anything useful. It's just to illustrate what happens when a process is terminated by a signal. Let's have a quick look through the code. We fork, and if we're the parent, we immediately wait for our child to terminate and collect its exit status. Using some of those macros we looked at, we test first of all to see if the process exited normally. If it does, we print out the exit status, the exit code from the program. We also test to see if the child was terminated by a signal. If so, we print out the signal number, and then we use this little convenience function called strSignal, which will give us a short text description of that particular signal type. Now we're going to explore several behaviours in the child. The child prints out its process ID, and to begin with it just sleeps for 3 seconds and then exits normally with a fairly arbitrary exit code of 5. Now if we save that and we build it, and then we'll run it, we'll see the child reporting its process ID, and then 3 seconds later the parent is reporting that the child exited normally with the exit code of 5. So what we're seeing here is the output from this line of code in the parent. Okay, well of course there isn't a signal in sight at the moment, so let's modify the child to generate a couple of self-inflicted signals. First, we'll generate a sig-seg-v. That's easy to do, something like this. What I'm doing there is I'm taking the value 0, casting it to be a pointer, and then trying to write a value there. Now the address 0 is not a valid address. So we'll save it, we'll rebuild it, and we'll run it again. And now you'll see we immediately get the parent reporting that the child exited with a signal number 11. And the strSignal call, that one there, is the one that's returning this little description of the signal. And we're getting a segmentation fault as we expect. We're not allowed to write to address 0. Let's try something else. I've got 3 integer variables declared a, b and c, so let's set a to 1, b to 0, and then let's try dividing a by b. You can kind of tell where this is heading. So we'll rebuild the code, rerun it, and this time indeed it reports a floating point exception signal as signal number 8. It's a little odd, I agree. The signal name is called floating point exception. We're actually doing an integer division here. Now let's have a look at the case where we generate the signal externally. So I'll simply put a pause in there, which will cause the program to block. Save it, rebuild it. Now if we run it, the child reports its process ID, but nothing else is going to happen now unless I make it happen. So let's go over to another window here. What we'll do is we'll send a signal using the kill command. We'll send a term signal to that process, 4686. And if you look over in the left-hand window, then the parent has reported that the child has exited with a signal number 15, a sig-term signal. Now, as you may be aware, the shell itself also reports the case where a process gets terminated abnormally by a signal. Just to demonstrate that, let's try running a program directly out of the shell. Let's run, say, sleep for 100 seconds. Come over to the other window. We'll try and find the process ID of the sleep command. There it is. And we'll send, let's say, a hang-up signal to that process. And if you look back over in the left-hand window, you will see that the shell has reported that the process was killed with a hang-up signal.